Section 5.3 is where the fundamental theorem of calculus is discussed. Okay, and as the name suggests, this is a very important theorem from this course. It really is the theorem that ties together all of what we've done about derivatives to this new concept, new to us, concept of integration. It tells us the connection between those two, and it's coming out of this course with an understanding of the fundamental theorem of calculus is hugely important. Now, for the purpose of this video, I am not going to introduce the fundamental theorem of calculus. I'm going to assume that you've read a statement of that, and I'm going to use these two examples to illustrate the two versions or two parts, as they're labeled in our textbook, of the fundamental theorem of calculus. Now, this first example, 41, involves what our textbook refers to as the fundamental theorem of calculus part 2, and it's the version of that theorem that by far will be using more often for the remainder of this course. And it's what people tend to think of when that theorem is discussed as the fundamental theorem of calculus. Here we have a definite integral of the function 1 minus x times x minus 4 for the interval from 1 to 4. And we talked about before how we can think of that as the net signed area for this function over that interval. We don't need to see a graph of this to calculate this value. And we're no longer estimating Riemann sums here. Here we are actually finding the exact net area. Okay, now important thing to understand, we've learned these antiderivative rules, which are a key part of this process. But unlike our derivative rules, we're at a point where we're pretty limited in what we are able to do. Okay, we have a product here, but we haven't learned anything that's, an antiderivative version of the product rule. That's not something that we've seen. So here's what we need to do when we have something like this. Okay, a product of these two binomials. We multiply them together, and you'll remember doing something similar to that when we were first learning about derivatives, and we had limited techniques then. So before we had the product rule for derivatives, when we're dealing with polynomials, we can just multiply and avoid any need for the product rule. Well, similar type of thing happening here. If we see this, we want to just keep in mind we can multiply, and then we have something that we can work with. The power rule for antiderivatives says that we'll increase the power by 1, divide by the new power, and we're going to go through this term by term, just as we would for derivatives, because with antiderivatives we still have a sum rule, a difference rule. Okay, so when applying this fundamental theorem of calculus part 2, what we need to do is find an antiderivative of the given integrand. Now, you'll notice I didn't write plus c here. And that's because when we're doing this, we simply need an antiderivative. We don't need the most general form of antiderivative. We just need an antiderivative. So typically when you're doing this, you don't write a plus c. If you do write the plus c and proceed with that, it's not going to hurt anything, because you'll have a plus c and you'll have a plus c and you'll subtract. But there's no need to write a plus c when you're doing a definite integral. Okay, fundamental theorem of calculus part 2 says now once we have our antiderivative, we substitute in the two limits of integration, take the difference, And that 4.5 represents that net signed area for this function over this interval. Okay. Again, exact, not an estimate like a Riemann sum would give us. All right, 71 is less typical of the type of problems you're going to see in this section and going forward, although we do have a little bit of this. And this involves the fundamental theorem of calculus part 1, which says that if I cover up this d dx part here and just look at that integral, we refer to something of that form as an area function. Notice the upper limit here is an x, so that means that that expression, again, ignore the d dx for the moment, that expression is an area function. It depends on x. So if you plug in x equals 4, that means the upper limit is 4. That'll give a certain answer. If you say x is 10, or your upper limit is 10, you'll get some other value. So it's a function of x. And this question is asking, what's the derivative of that area function? Well, the fundamental theorem of calculus part 1 says that this area function is an antiderivative of its integrand. So that means when you take the derivative of it, you just get back to that integrand, although it's going to be in terms of x, because this is a function of x. And so that's all we have to do in a problem like this. And that might seem like, well, gee, all we're doing is getting rid of the integral, and we're changing the variable to x, which is in practical terms, that is what we're doing to get our answer here. But what I want you to understand about that is this is telling us that the process of taking a derivative and taking an antiderivative or evaluating this integral that represents this area function, those two things are essentially inverses of each other, inverse processes. So they essentially cancel each other out, which is also could be said about the fundamental theorem of calculus part 2. There's some sort of cancellation between these two processes, and that's a kind of simplified way of describing what's happening, but it is describing a relationship between derivatives and integrals, and that's what the fundamental theorem of calculus is all about. So that's how that one works. I hope you found this video helpful. I will see you in the next video.